Chapter 9, Section 10, Part 2, Taylor and Maclaurin series, error bound. In our last lesson, we learned how to create power series representations, expansions, using methods outlined by Maclaurin and Taylor. We also introduced the idea of a Taylor polynomial approximation for a function. In this lesson, we will look at how we approximate and bound the error of an approximation found using a Taylor or Maclaurin polynomial. If f of x is equal to t sub n of x plus r sub n of x for degree n Taylor polynomial t sub n of x, then r sub n of x is the remainder of the Taylor series. If the limit as n approaches infinity of r sub n of x is 0 for all x in an interval convergence, then f of x is the limit as n approaches infinity of the nth degree Taylor polynomial. For an approximation using a Taylor polynomial, in other words a Taylor approximation, we want to bound the value of the remainder r sub n to determine the error for our approximation. We will consider two error bounds, the alternating series error bound and the LaGrange error bound. First, the alternating series error bound. For a convergent alternating series, the error for any partial sum s sub n is less than the absolute value of the n plus first term, i.e. a sub n plus 1. That is, the difference between the infinite sum and the finite partial sum s sub n is less than or equal to the absolute value of a sub n plus 1, the next term in the series. Therefore, if our Taylor series is an alternating series, then the difference between the value of our infinite Taylor series and our Taylor approximation of degree n is less than the absolute value of c sub n plus 1 times x minus a to the n plus 1, where c sub n plus 1 is the n plus first derivative of f evaluated at a divided by n plus 1 factorial. Let's consider an example from the AP examination. The function g has derivatives of all orders, and Maclaurin's series for g is given as the sum from n equaling 0 to infinity of negative 1 to the n times x to the 2n plus 1 over 2n plus 3. The Maclaurin series for g evaluated at x equals 1/2 is an alternating series whose terms decrease in absolute value to 0. This fits one of the hypotheses of the alternating series theorem. The approximation for g of 1/2 using the first two non-zero terms of this series is 17 over 120. They would like us to show that this approximation differs from g of 1/2 by less than 1 over 200. Since we meet the hypotheses of the alternating series theorem, we can start by saying, by the alternating series theorem, that g of 1/2 minus the degree 3 Maclaurin polynomial value of 1/2 is less than the next term, c sub 3. c sub 3 is negative x to the 5th over 7, and for x equal 1/2, c sub 3 would be negative 1/2 to the 5th over 7, or negative 1 over 224. Therefore, by the alternating series theorem, we can say that g of 1/2 minus the degree 3 Maclaurin polynomial evaluated at 1/2 is less than the absolute value of negative 1 over 224, which is 1 over 224, which is indeed less than 1 over 200. Therefore, we have shown that this approximation for g of 1/2 is less than 1 over 200 away from the actual value. Taylor's theorem, also known as the LaGrange error bound. Let f of x be a repeatedly differentiable function on the interval I containing a. Let t sub n be the degree n Taylor polynomial for f centered at a. If there exists a real number k such that the n plus first derivative of f at x is less than or equal to k for all x in the interval, then the absolute value of the difference between the function f of x and the Taylor polynomial approximation of degree n is less than or equal to k over n plus 1 factorial times x minus a to the n plus 1 for all x in the interval. At first look, this is an overwhelming theorem, but let's look at it more closely. The key to applying the LaGrange error bound is to understand two key facts in the hypothesis and apply these facts to find a value for k. First, f of x is a repeatedly differentiable function on I. Therefore, f and all its derivatives are continuous on the interval. Second, k must be the maximum value of the n plus first derivative of f on the interval, or greater than that maximum. This gives us two equally valid ways to find k. If the interval is closed, then the extreme value theorem guarantees us that the n plus first derivative of f must have a maximum value m on that interval. If we find this m, then we can let k be m. If we are familiar with the graph of the n plus first derivative of f on I, then we can identify a value b that bounds that n plus first derivative from above. In that case, k would equal to b. An example of this would be if the n plus first derivative was a sine or cosine. We would know that that function is bounded above by 1. With an understanding of this process for finding k, let's consider some examples from the AP exam. Let f be a function having derivatives of all orders for all real numbers. The third degree Taylor polynomial for f about x equals 2 is given by 7 minus 9 times x minus 2 squared minus 3 times x minus 2 cubed. In part C of this question, students were asked to use this third degree Taylor polynomial to find an approximation for f of 0. In this case, it's negative 5. In part D, we were told the fourth derivative of f satisfies the inequality that the absolute value of the fourth derivative of f is less than or equal to 6 for all x in the closed interval 0 to 2, which includes 0. They want us to use the LaGrange error bound on the approximation for f of 0 in part C to explain why f of 0 must be negative. Since we know the fourth derivative is less than or equal to 6 for all values in the interval, then we can let k be 6. By Taylor's theorem, we can say that f of 0 minus the third degree Taylor polynomial at 0 is less than or equal to 6 over 4 factorial times x minus 2 to the fourth. Simplifying then, we find out that the difference between the function at 0 and the third degree Taylor polynomial at 0 must be less than or equal to 4. And f of 0 minus the third degree Taylor polynomial at 0 must be between negative 4 and 4. Since the third degree Taylor polynomial at 0 is negative 5, we can say that f of 0 must be between negative 9 and negative 1. And therefore, f of 0 must be negative. Let's consider a second example. Let f be a function given by f of x equals the sine of 5x plus pi over 4. And let p of x be the third degree Taylor polynomial for f about x equals 0. Again, this is the Maclaurin Taylor polynomial. Let's find p of x, and then let's use the LaGrange error bound to show that f of 1/10 minus p of 1/10 is less than 1 over 100. First, f of 0 is equal to the sine of pi over 4, which is root 2 over 2. The first derivative of 0 is 5 root 2 over 2. The second derivative of 0 is negative 25 root 2 over 2. And the third derivative of 0 is negative 125 root 2 over 2. Therefore, p of x is root 2 over 2 plus 5 root 2 over 2x minus 25 root 2 over 2 times 2 factorial x squared minus 125 root 2 over 2 times 3 factorial x to the third. Using the LaGrange error bound, we can now show that the fourth derivative of x is 625 times the sine of 5x plus pi over 4. Since sine of x is less than or equal to 1, then 625 times the sine of x is less than or equal to 625. Therefore, we can safely say the fourth derivative of x is less than or equal to 625. We'll let k be 625. Therefore, f of 1/10 minus p of 1/10 is less than or equal to 625 over 4 factorial times 1/10 minus 0 to the fourth power. Simplifying, we therefore get that this is 1 over 384, which is less than 1 over 100. Therefore, we can safely say the difference between f of 1/10 and the Taylor polynomial at 1/10 is less than 1 over 100. That concludes our video.